we're still missing quite a few people who have signed up. Now that clock says it's 1 minute to 7, but it has, but it happened. 7 o'clock? All right, well, then we're going to start. They'll come in late. Most of them will probably still be here in time to hear our 2 lecturers. I want to take just a couple of minutes and set the stage of what we're trying to do in this course, and then I will introduce our first speaker. This course is all a continuation of something we've been working on here now for several years, and that is to take a look at the Southern California Bight, the area that goes from up there, just north of Santa Barbara, yes, Point Conception, down to the U.S.-Mexico border, and actually goes a little into Mexico. Over 22 million people live along the coast in this area. We've got the 2 largest ports in the United States. It's really quite a remarkable place. And what we're trying to do is to explore whether or not this region could be an international model of how you can use science and technology in conjunction with a strong ocean ethic to both protect the environment and coastal and ocean ecosystems and still use the ocean in appropriate, responsible ways to benefit the economy. So if you look at this, it's very clear that there's no place in the world that can rival the oceanographic research capacity we have in Southern California. Much of it is concentrated in San Diego at Scripps, but there are also significant programs in other universities, Cal State Long Beach, UCLA, USC, UCI, Caltech. It's a remarkable place. No place in the world has the oceanographic expertise that we have concentrated in this area. It's also the leader in ocean technology in the U.S. If you look at the number of high-tech ocean technology firms that we have in the greater San Diego area, it is greater than any place in the United States. And if it's not number 1 in the world, it's within the top 3. It's a leader in ocean engineering, in our capacity to understand and come up with solutions, to build things, to protect the coast, to build offshore facilities, whether they are offshore renewable energy or whatever. It's an ocean that's rich in resources, both living and non-living. This is, according to the TOP program, the tagging of Pacific pelagics. This is what the area of the Pacific Ocean that is used by more marine life across different sphyla than any other comparable place. And we've got 10 billion barrels of oil off this coast, 14 trillion cubic feet of natural gas. And it's a very forgiving piece of the ocean. Because of the oceanographic properties, deep water close to shore, strong circulation, the water in this area gets renewed every few days. Quite unlike other systems that I've studied, like Chesapeake Bay, where the renewal time is the order of a year. So this is a forgiving piece of ocean. All of these are assets that go along with this wonderful ocean ethic that we have. And so our hypothesis that we want to test in this course is that we could use this knowledge and technology not only to protect the ocean, and we've done a pretty good job with 50 marine protected areas, but we could also use it to use the ocean responsibly for sustainable industries, whether it's offshore aquaculture, offshore renewable energy, and that we could then benefit the economy. And some of you in this room participated in a forum that we did in July to explore this idea. We asked the question, what qualities do you want the Southern California Bight to have in 2050 and 2100? We surveyed over 150 people. The 2 qualities that were tied for number 1 were to have healthy, productive coastal and ocean ecosystems. And tied with that was to have a healthy, robust, diverse ocean economy. I wasn't surprised at the first that I mentioned. I was surprised at the second. And then the third quality that people voted for was that they wanted to have healthy communities. And one of the measures of health was they were economically healthy. So then we asked the question through scenarios, will continuation on the present trajectory lead to a future that has the qualities that you want, that you said? And the unanimous conclusion was no. If we continue on the present trajectory, we will not get to the future that we want to have. Then you ask yourself, are there disruptive strategies? Strategies that will move you off the existing trajectory onto a new trajectory that would get us closer to a future that would have the qualities you said you want. And among the strategies, the first disruptive strategy was you have to reform, streamline, make more transparent the permitting process. That was number one. And then there were a number of others that followed from that. And so what we want to do is test the hypothesis whether we could become this international leader. And over 4 weeks, we're going to look at different dimensions. Tonight, we've got two distinguished people who are going to convince you, I hope, about the world leadership that we have in ocean science, oceanographic research, and also in ocean engineering. And then next week, we're going to look at policy and conservation, and then we'll go on to different topics. And there's one other factor that should be on this list, and that is we have the world's greatest aquarium. So John, don't tell me. don't tell Nigella at Birch that I said that, okay? All right. So, and this, you already have this, I think, in your notes, but it's quite a remarkable group of people you're going to be meeting over the next 4 weeks. And as you know, we keep these courses small so that you can interact with our speakers. And our first speaker is going to be John Orca. John is a distinguished professor of geophysics at Scripps Institution of Oceanography at the University of California, San Diego. He's been there for 40 years. He's a distinguished researcher at the San Diego Supercomputer. He has a BS from the U.S. Naval Academy, an MS from Liverpool University in England, PhD from Scripps, and he's one of the leaders worldwide in many different areas of oceanography. Recently, last year, he was elected to the National Academy of Engineering as a recognition of his contributions. He was also designated as one of USC San Diego's 100 most influential alumni. He was the president of the American Geophysical Union, secretary for the Navy, chief of naval operations, oceanography chair, won the Maurice Ewing Medal, and it goes on and on. You've got two remarkable people, and I'll introduce Dilip when he's going to speak. So take advantage of what they have to say and be thinking about testing the hypothesis. You can never prove a hypothesis. You can only disprove a hypothesis. But we want you to be thinking so that by the end of this course, you're either going to feel, yes, we have this wonderful opportunity that we should seize, or no, it's just not in the cards. All right, so John, come on up, and then how do we go from, Keith, you turn mine off, and John, are you wired?
I am.
You are wired. All right, please welcome John Orca.
Third. Yeah. And I think, I'm online. Thanks very much. And thanks for the introduction. I am at Scripps, have been for some time, as you just learned. And I'm going to talk a bit tonight about science that plays a big role in the Southern California bight where we work, which was described just previously in the talk. And I think both Dilip and I would like to answer questions as I go through this rather than waiting until the end when everybody's forgotten what they wanted to ask about anyway. So if you just interrupt and please do. I can answer well, I'll try to answer questions that you might have as a result. That's our pier, and we've used some conventional sorts of technologies. We have 4 ships, 2 of them quite large. The 2 on the left, the Roger Revell, the Melville, which is the oldest, built in the 60s, and is now being about to be replaced by a new ship, are ships that go around the planet. They're global class ships. They go down to Antarctica, into the Arctic, spend a lot of time in the Western Pacific and in the Indian Ocean. The others are smaller, tend to work mostly in the Bight itself. Then we have a really weird ship. It's actually a platform called Flip, and it's a semi-submersible. I'm a submariner, actually. He caught that Annapolis business that he talked about, but I started my career as being a submariner, and this is kind of like a submarine, except hopefully that bit never goes underwater. This is it upright, and this is just finished flipping into the vertical position, and the background here is the Flip sitting in a floating dry dock being repaired. But it's now just a little bit over 50 years old, which is an awfully long time for a ship, but it's still going to see doing a lot of really interesting work. Because it is this vertical system, it stays very stable in the ocean. The waves go up and down around it, but it pretty much sits still. It makes a great platform for doing research.
What's the purpose of the platform ship?
Sorry?
What's the purpose of the platform ship?
What's the difference?
No, the purpose, sorry.
Permit?
What's the purpose?
Oh, the purpose, I'm sorry. Well, when it was built with Navy funds back in the 60s, and at the time it was used for understanding acoustics in the water. But now it's used for a lot of different reasons. Sometimes acoustics. It also has turned out to be a really good ship or a platform for putting hydrophones in the water and listening to marine mammals, tracking them, understanding individuals, and differentiating between these things. So there's a wide variety of things that it now does. Anyway, I'm going to talk a little bit about the Southern California Coastal Ocean Observing System. This is a project that does a number of things. There's a website, it's called scoos.ucsd.edu, and it deals with ports and harbors in the area, particularly the big ports up here. It measures currents, winds, and sea level, waves. We have an oil spill response approach, which I'll show you some example, in search and rescue. You can see the entries from the south into the west for the shipping into Los Angeles and Long Beach in red here, and the little dots around there are areas that we continuously update every hour with wave conditions for information for ships coming into port here. So those are the things we do. We have a bunch of partners. I started it about 12 years ago and cajoled a number of other institutions to join, starting with Cal Poly San Luis Obispo up in the north, UC Santa Barbara, JPL, UCLA, Cal State Los Angeles, UC Irvine, of course Scripps, and then down the SQUIRP, Southern California Coastal Water Research Project, the UNAM that is in Ensenada, and CICESE Research Institution nearby in Ensenada. So those 11 institutions support the program. We seek funds to support them in turn and keep a number of operations going. One of the really interesting ones now is the Coastal Occurrence Monitoring Program. And with California funds, which are kind of rare these days, but 4 or 5 years ago, the state of California gave us $21 million to put these monitoring systems, high frequency radar systems along the entire coast in California, starting down south of the border in Mexico and going all the way up to Northern California. But what these do is actually measure the wave heights in the area. We have recently, with the governor's initiative, signed an agreement in which the 3 observing systems that are shown here are now collaborating with each other and working with each other continuously just up the coast in Central California, Senku, Central and Northern California, and then NANU's North America coastal observing system. So we now are able to extend the size of what we've done in the Southern California bight up along the entire west coast. The network looks like this now. I showed you that map before, and you can see each of these dots here represents a coastal system that's capable of measuring waves. And subsequent to this, the East Coast has started to build out, and I'll show you a little bit more soon about the Gulf of Mexico, which appears to be relatively bare. Yes?
These are land-based?
They sit on land and they look out at sea, so they're fairly straightforward to maintain, but they can look out about 100, 120 kilometers, so, or 50 miles out in the ocean, 60 miles into the ocean, and actually measured waves, currents, that is, in the ocean offshore. And how's it work? Basically, you've got radio waves, literally high-frequency radio, travels out to the wave tops here, and then scatters back here. And just like using Doppler, you listen to a train coming, the frequency shifts higher. If the waves are moving toward you, the frequency of the outgoing waves increases here, and you can then measure the radial velocity away toward or away from the station. And if you've got a lot of these along the coastline, you can actually, because they overlap each other, you can determine what direction the currents are actually running. It's really handy for sailing. If you do the Ensenada Newport race, one thing that people do carry along now is the wave maps, because it gives you such an incredible boost in that competition. There's a national search and rescue network now that started after we got this system in Southern California working in these various data nodes. This is the one at Scripps, but these pink things here go over to a search and rescue experimental program at University of Connecticut. It goes to the U.S. Coast Guard here for information. The system on the East Coast is run by Rutgers University, and these networks basically operate in real time to send wave estimates all along the U.S. coastline to Search and Rescue and the Naval Data Buoy Center, or National Data Buoy Center, which is a NOAA organization down here that collects all the data and mirrors what we do in Southern California for the entire country. So this is an example of things that we've been able to do in California. California got us started, and it's become a national program now that's of considerable utility. This is a fairly dull slide. It's just what we've done, because the California coast is so long, people working at Scripps or in Southern California bight even don't have the time, can't afford to go up to Northern California and make repairs. And so we have sites all on the California coast now that are aggregators of data, like this one, SLO, is San Luis Obispo, and they have about 9 stations they're responsible for. They do the maintenance on those things. They make sure the data flow is happening, and then we concentrate the whole thing at Scripps and then put it on the national network. And it happens virtually instantaneously. I should have shown you this. This is one of those radar systems, if you will. It's a high-frequency radio. And, it has 4 antennae on it that allow it to beamform out at sea to measure specific parts of the ocean surface. Should have gone back. Anyway, a good example of search and rescue and the use by the Coast Guard, shown in this map here, it actually is You might notice this is Long Island up here, but this was an exercise, not an exercise, this was actually an application a couple of years ago. This is what one did in the early days before there was surface current information, and this is basically, the red represents the preferred target. That is, if you were going to go look for something that had gone in the water some time ago and wondered where it was at the moment, you would look in these red areas first. When you add in the high frequency radar, shown over here, it decreases the size of that probability patch by a large fraction, so that you narrow down the targets and the areas that you actually have to look for. And they just show you what these are. It's almost 11,000 square nautical miles, and this thing collapses to about 3,500 square nautical miles just by using that information for search and rescue. And the same thing, of course, is done for tracking oil spills. This is an example. There's a state program called Osprey that we work with. This is an oil boom just being demonstrated in the bay. But we have, we'll see, remotely operating gliders that operate off the coast, as well as the surface radar. And from a spill, a hypothetical spill at a offshore production site, we're able to project where the oil would actually move during the next several days, so that if you're trying to corral the oil at sea, you've got a good tool for making that happen through this system.
Would you actually be able to see the oil spill, or just think about where it's going?
Think about where it's going.
Yeah, okay.
This thing has no capability for seeing. Seeing is done like, this is the spill in the Gulf of Mexico here, and this is a radar map off the Gulf of Mexico here. This is a translation of it. These strips here are taken from a panchromatic satellite flying overhead. This one actually turned out to be a classified system that was declassified to let you see where the oil was moving as it moved away from the spill area in the Gulf. The really interesting thing was that when we began this, when that oil spill occurred, all the systems that had been installed in the Gulf of Mexico were down. There was not money available to maintain them, so there were none of them operating. And so the team that we have in Southern California flew down. In April, there were no systems operating. April 20th, by the 1st of May, the systems were operating off Louisiana and Texas. And then on April 24th, we got southern Florida back up so that we began to map better the oil spill in the Gulf of Mexico. So again, this is things that California does, and we have a lot of expertise in it, and it's been used with good effect in lots of places.
Did I understand you correctly that they stopped maintaining them
Yes,
because of lack of funding?
yes. It's not uncommon in government today. I represent a university which has this very same problem today. And one of the things that we did that was very successful was the Hyperion outfall had to be replaced and rerouted in 2006, and so we monitored that very closely with the radar and with autonomous vehicles in the water, so that we were able to keep track of the pollution that actually flowed out of the system during that period of time, and track where it was going as it moved down the coastline. It didn't come back ashore, but it was you can't not do it. You know, you've got this system that's no longer performing. It can't be used. You know, a whole city over here needs to have an operating sewage system, so you had to take the whole system down for 2 weeks and lay an entirely new run of pipeline out here. Not a very pleasant job, but at least it's possible to know how much of a problem that's going to become as you're involved in the project. So it's dirty work, but it's you know, it does make good use, I think, of the capabilities that we do have in Southern California. This is a picture of the Santa Monica Pier, and one of in the bight and all the piers now, there is a tsunami gauge that allows you to watch tsunamis come ashore. The raw record is shown here. These things that go up and down are the tides, and removing the tides, you get the green thing down below, and you can see the height of the tsunami is about 2 feet after as it rumbled through here. This is the 3/11/11 tsunami from Japan, the monster that unlike any tsunami we'd seen before. But this gives you an idea that we can measure these kinds of things. We measured much smaller tsunamis than this one by far. A lot of these displacements are frequently on the order of a centimeter or 2 in height, and you see them come by. But this was a record for us. And further north in Northern California, Washington, and Oregon, going up into Vancouver, there is exactly the same kind of fault that lies up there. This Cascadia fault it's called, and it hasn't broken since 1700. And so we're getting, it's been 300 and some years since that happened, and the reason that we know about that earthquake is not because the Indian tribes or something, but it's because the Japanese saw this tsunami. They called it historically the Silent Tsunami. These big waves came ashore, and no one knew where it had come from at the time. They were surprised at this, but it was from northern U.S. Harmful algal blooms are becoming more of a problem and issue in California now, and we spend a lot of time tracking. You can see the reddish water in here close to shore. And I think you've all seen it. Many of you have gone down to the beach just to watch the fluorescence in the evening from these things. Generally harmless, but there are lots of parts of the world when these things can become very, very toxic. And hoping that doesn't happen here, but as we continue to put lots of nutrients from cities into the ocean, we'll have more and more of these kinds of blooms at the time. This is kind of a projection to the future, if you will. This is the Southern California bight, which I showed you, or you saw it when you came in today with the topography. This is a satellite image or series of images of the temperature of the ocean. This is the thing that charges up when an El Nino happens, flowing from the western Pacific to the eastern Pacific here. But we are now in California continuously running models on the data that we collect from offshore. The radar data, autonomous vehicle data, ship data, winds and so on are being continuously integrated into models off the California coast. And if you go to that website I talked to you about earlier, at any one time you can see what the temperature, salinity, and so on in Southern California is during the last few hours, and it's continuously updated. And this just takes a look at the different kinds of tools that we're now able to actually put into a solution in a model. This is the Aquarius Satellite, and it actually is able to measure salinity in the ocean directly, which is quite a feat, and the reason for this big antenna. This is the fellow at JPL that made this slide for me, but this is Jeopardy, on which 2 people worked against Watson, which was the IBM large supercomputer here. And of course Watson, no surprise, beat the game. But the real point here is that we now have machines that are large enough to think about actually having a continuously operating ocean model from the surface down to the seafloor for all of the U.S. and potentially the entire world. So we're not limited anymore so much by the computational problem, but we're limited more by the data that we collect. Not every part of the country is as rich in real-time data as is Southern California. This just shows you one of the models, which is, here is starting to run. This is temperature. The little arrows here are the currents. This is the winds at altitude, 10 meters height, In this area, every one of these little grid spacings is the computation on which that scale is made. But this is what you see when you go to the website, so you can get an idea any given day what the water is likely to be. This summer has been fantastic, certainly in the further south in La Jolla for swimming and so on. These things up here, there's a picture of a thing called a glider. And there are three lines that are running off the coast here, and then little avatars for the gliders here that show you where the position the gliders are going in and out on these rays continuously. And these things are autonomous vehicles. They navigate by GPS when they come to the surface. They find out where they are. They can get commands to go somewhere, and they send the data they collect back to you. So they come back and fairly often here. So this thing is just sitting in the water off here, yo-yoing up and down, going in and out continuously in the ocean, making these measurements. Going along to getting back to the Long Beach pilots, I thought this would be kind of fun, but this shows another system that we operate called the Wave Buoys, and there are a number of these off the California coast. And what they allow you to do by these systems, they measure very accurately where they are with the sea, what the wave height is, what the direction the wave is propagating in. You combine all that data, you can project the waves coming in ashore to the size of the waves. The yellows are shown up here. You can see it very well, about 6 feet. Here green is shallower. You can see San Clemente here shields a lot of the incoming energy so that the wave heights are way down in the lee on these things. But the harbor pilots are very interested in how big the waves are offshore when they're doing their work. And the big super tankers are the same way. The draft on a super tanker is now so large that, and the sediments offshore are not deep enough. They're not dredged particularly deeply going into the harbors. So there's a problem if you have waves that are, if they're long waves, about 12 seconds between the points here. The deep draft vessels are standing in great danger of hitting the bottom. Yeah.
What is the draft of a large
Pardon?
super tanker? The draft of a super tanker?
Oh, it can be 30 feet, 40 feet. I mean, these things, when they're burdened, are very deep, and it's hard to dredge to keep that kind of thing open. It's just economically difficult. So they use this information about the waves so that they can stay outside and anchor in this area here and wait for the waves to clear and then go into port. But to keep a tanker at sea like that is about $100K a day to do that, whether that's full of cars or whether it's full of oil, whatever it is that they're trying to bring in. But they have no choice because you have to make sure you don't set that ship on the seafloor as you go into port. We have that wind model that I showed you comes from the Navy, actually, a partnership we have with NavAir here. They provide the winds, we provide the ocean model, and combine these two things together. But one of the things they like to do, test and do exercises with missiles offshore here off Point Magoo, and they like to have these things ride at least 4 feet above the wave tops. And so they're really interested in how high the waves are, and they don't like to ride down the trough either, because there's this huge chance if you miscalculate with that thing, it will actually go underwater, which is a bad thing to try to do. So we provide, this is a wave buoy here. These are wave buoys. There's a couple off the point up here. This is very large waves out here, greener, milder. And so they're able to check as well in doing exercises when the conditions are going to be about right for testing and operating offshore. This is it shows off the coast of California again here. The reds here are high currents, the greens and yellows are low currents. And again, it just makes the point that for search and rescue here, pulling people out of the water, having that data is critical. Another thing that we do in San Diego, we have two outfalls here, one off Point Loma and another one here off very southern part of California. And the discharge depth is 27 meters and 95 meters for these two. And we monitor that regularly with this other autonomous vehicle, which is actually propelled. It has a propeller on it that we can move it through the water. That's what it looks like on the back of the boat that deploys it. It can measure a lot of things, conductivity, temperature, and depth. It has optical sensors for measuring the density of organics in the water. And this just shows you what a couple of the sensors look like. What you're doing is looking for this decaying organic matter in this area to measure the levels. And one of the things that can happen with these outfalls is that the ocean is stratified, and it's possible using one of these autonomous things to measure the temperature here, which translates directly into density, so you know exactly where it is. That plume is likely to be extending offshore, so you can sample at that depth, concentrating that, but you can never see it on the surface. There's a buoy out here measuring, and it measures from the surface to the bottom. Here, these are the directions of current, and if you look at this is at that Point Loma outfall. During this period of time, the discharge is predicted to go directly south. Sometimes it doesn't, though. Sometimes the eddies come through this thing, and it changes the circulation to the north, and then beaches close. Well, got a little bit of time here. I want to go a little further here because it's a thing I find very interesting, and a thing in which we are again extending a lot of these technologies to the Arctic. This shows the ice extent here in square kilometers through a summer minimum. This is a average over 1979 to 2000. The ice extent was fairly high. This summer, this shows you what the ice did this summer, and it's set an historic record for ice coverage. Then that is lack of ice coverage. This is a picture I just got from a guy that just came back from mapping up there. If you look at this latitude and longitude, this is 2007, and the date is 9/6/2007. Same location, almost the same time. This is what it looks like in the Arctic. Another picture. This is again 2007 here, and this year, this is what it looked like. So it is a world changing rapidly. And one of the interesting things, policy-wise, is this shows a very large ship called the Polarcus. And these are some of the details. It's there are 8 ships like this in service. There are 2 ships of this design, and what they do is tow streamers for oil exploration. The officers are in Bahrain. They have large diesel electric plants, 12.7 megawatt diesels. You can break a meter of ice, which you can't actually make any measurements through ice, but you can pre-position. The idea is that this fleet can be pre-positioned when that summer happens and go in there and explore for oil and gas. It was just a kind of public policy that is very problematic because the ice is clearing, obviously, in the Arctic because we're putting more and more hydrocarbons and CO2 in the atmosphere. And we have a positive feedback system working here, and positive doesn't mean good. It means when you have more of something, you have more of something else. And as the sea melts back, there's going to be more and more exploration and extraction of hydrocarbons and burning of fuels that's going to accelerate the process so that the Arctic will go become open much earlier than we had previously thought it would. This is just one small example, but sometimes it seems like we don't think. But this shows the extent of the ice cap during the wintertime here. This is what it looks like during the summertime. So an awful lot of it disappears. And one of the important things is there is a thing called multi-year ice. And it is thicker than the others. And you can see that the 4-year ice here, as time has gone on, has almost disappeared. Even the 3-year ice is not very prevalent anymore, but almost everything in the Arctic is now 1-year ice, and 1-year ice will disappear every summer in the not distant future, and the famed Northwest Passage will become a reality soon. A program I work in, I'm one of the lead PIs, principal investigators on this, and this started about a decade after the SCOOS began, and we are now putting marine systems in the ocean off the coast here. This shows a cabled system here, some buoys on this part of the U.S., and making these kinds of measurements continuously in various environments. Here, a bunch of buoys. This is off the coast of Massachusetts, where this is located. This particular one is off the coast of Oregon. This is out on the, well, both of these are out on the mid-ocean ridge, about 400 kilometers offshore. But these are sending data back continuously all the time, in real time. Not yet. The systems haven't gone in the water. The part that I am running is the cyber infrastructure part of this that seeks to put all the data together to bring everything back ashore and distribute it to everybody openly in real time, within about a second of the time it was collected at sea. And this will be, I think, a new kind of model for these. It follows directly upon the work that's been done in California with the Southern California Coastal Ocean Observing System, but will allow us to extend these observations to many other parts of the world. And the one innovative, I think, a very innovative part of this is this just shows the network that we're using here. But this is the part that's actually out at sea, and this is an instrument, this is an instrument, this is an instrument, for example. And each one of these things has a box and a set of software that makes the data that come out of this end look exactly the same as data from any of the other 780 sensors that are on the system, so that we have an interoperable system that we can collect data from all these things readily and make it available to people. And the fact that it's basically on the Ethernet, we can also use it to command these systems at sea. So I think I've gone a little further than I had expected I would. This is an interesting part of this. It's a program we've done with the cyber infrastructure, the Ocean Observatories Initiative, and with NOAA. We've built a system on a cloud that's operated by Amazon, the people you order your stuff from right here. But they have a lot of excess storage capacity and compute capability, and we buy it for a pretty low price. And all this data management is done in the cloud on the Amazon EC2. And we output things like Google Earth and stuff through a program called MapLab and other things in ways. So rather than trying to make everything the same, standardizing, there's a Tower of Babel in terms of the way that people make data available. We convert the data to whatever system that you want to personally use so that you can use it without a lot of overhead and work. And that, I think, is quite a departure. This is a fun thing that I'm involved with, and it's called ADOS, but this is a glider, a wave glider, however, and I'll show you how this works. One of the the features is that you really substantially reduce the ship costs for doing this, but it actually acts as a telemetry data mule, if you will, for moving data from the seafloor here to the glider to a satellite. And these things can swim autonomously for thousands of kilometers, and once there, they can hold station within a city block of the location on Earth. It's propelled entirely by wave power here, so that there's no real power source necessary. And this shows you how it works. This is taken from below. That shows the surface. This is the thing that actually does the tugging. It's a set of vanes. When the waves go up, it tugs on these things and pushes that thing forward. And then when it dives, the vanes snap the other way and keep pushing it forward. And it goes about 1.5 knots every day, continuously, all the time. Here, that's the system we're using. This shows you that it has a pretty good tug. So you can see that there's not big waves either. It's fairly small waves. So this is a little company in California, Liquid Robotics, that does this. We built a bottom package, or we're not building, we're going to test this bottom package this year, but it has an instrument ball in the center here so that we can actually tow the whole thing out thousands of kilometers, put the sensors in the ocean, and continue to bring back data and the glider later on. We tested 2 of these this last year in the Arctic. This shows, this is off Barrow, Alaska. This shows the ice, and we had 2 of them following each other in this triangular pattern, measuring the temperature of the water. And one of the things we saw in a snapshot that came back was a little piece of ice sitting off the port bow. And when we got the gliders back, both of the gliders had, their noses were pretty beat up by running into pieces of ice during the summertime there. But they survived. They sent data the whole time. Very interesting data. Off Barrow, between that and the ice, the temperatures got as warm as 52 degrees Fahrenheit in the water, which is and not very close to freezing. That takes a lot of energy to get that back out of the water. This is the glider network that I talked about. We have 4 of these running offshore. Get a good idea what it looks like. Since we started in 2006, they've covered 130,000 miles over ground and 142,000 kilometers through the water. Lots and lots of days of data collection. But because they're autonomous, they're self-propelled, they don't have people involved, they just keep doing this work year in, year out, bringing back data. You don't have to bring the ships out. Sorry?
I have a question
Yes.
about that. It seems that as well as getting temperature and wave height, that perhaps these could also be used for sensing within the water, such as marine mammals. And I know that's a problem for shipping and knowing where to have the ships go. Do they do any of that?
There are some experiments doing with along those lines. I mean, this shows some of the things that we measure, temperature and salinity and so on, and those are easy because they don't take a lot of power. A hydrophone and all the data it generates takes a lot of power, and so we have problems with bits transmitted per joule of energy available to us. And right now, the combination of a hydrophone, the necessary electronics and transmission of data, we just don't have what it takes to make that work over a long period of time. But time will change that,
Someday.
so that it will be possible to do that.
Do these gliders, are they on the surface?
Sometimes,
I mean, they have the ability to dive and so.
yeah, they basically yo-yo.
Okay.
You just can't see each other yo-yo, but they go down and spend a day or so, and then come back up and transmit data, find out where they are.
You ever
They can
lose any of the
adjust.
ship traffic? I mean, just, you know,
We've
they're
never-
randomly moving around and the ships are just passing through.
It's a big ocean.
Yeah, okay.
It's a big
Yeah.
ocean, so not a problem. At least it has never been to date.
Yeah.
Okay, I think I better quit here. I think I've shown you most of the goodies that I had, that I
John,
brought along.
I'd like to come back to the Southern California bite. I tried to copy down a statement. This is pretty close. You said, not every part of the ocean is as rich in data as the Southern California bite.
Right.
And in a relative sense, if you compared other coastal areas in the United States to the Southern California bight, are there any that are as well-known as the Southern California bight?
I think one area is probably off New Jersey, near Rutgers. Rutgers is a very active group, and they started after we started, but they've done a lot of really interesting things. And so I think
So maybe
that's the other hot spot.
Right. But we clearly are, we're leaders in having the data and in oceanographic research, technological innovation with all of these things. So a couple of years ago, as you know, the Hub SeaWorld Research Institute proposed an offshore Finfish aquaculture program a little north of San Diego. They spent $1 million, 18 months, and they gave up because they couldn't get a yes or a no from the state in getting a permit. They went 25 miles south into Mexico, and they now have a farm there. Was the reason because we don't know enough about our coastal ocean that they went to Mexico?
No, it's because we have a regulatory system that just doesn't work.
Thank you.
It's just too cumbersome.
Okay, let's see. Point Loma. One point. My impression is, or my recollection is, that there are two major cities in the United States that have this ocean outfalls that do not comply with full secondary treatment.
Mhm.
Point Loma and Sand Island in Honolulu.
Right, right.
And say a word about that.
Well, it's been a long history, and it's been tied directly to the institution, for better or for worse. But it is true that that's Point Loma outfall that I showed you is not treated to third stage, whatever.
Not
That's
the full second.
normally required. We get an exception about once a decade to do that, but the reason that this has happened in the past is that there were ongoing continuous data about the impact of that outfall that the city was able to use to show that the impact was not substantial from that particular thing. So, I mean, that makes a big difference. I mean, it's, if you're trying to work in an area that has no data, you're going to have a very hard time getting through the regulatory system.
You had to.
Yeah, I was just gonna say, would you look at it as a problem of the regulatory issues, a problem of not working together with industry, the sciences, and everybody trying to come together, and it's more of a politician issue, and they're trying to decide, like in education, we always say that, you know, we know what's going on in the classrooms, but the politicians seem to decide what's gonna happen in our classrooms, kind of thing.
I think that's part of it, but part of it is just the numbers and different goals of the various regulatory agencies. They're very independent. Some of them overlap a great deal, but in order to do something, you have to get everybody on board, and that can just take years and years and years. So it's not simply politics, which plays a role. It's just simply we've created a bit of a monster here with overlapping systems for managing the ocean off the coast, and we need to make it more straightforward. And it wouldn't hurt to have a few scientists on the boards, which is generally not true.
Larry?
Is there any other place on the planet, any coastal area that's as data rich? Scotland or something?
No, Scotland's a tough area. What? No, I'm trying to think. I mean, there's an awful lot of work in Europe, and there are probably good examples in particularly the Baltic, where there's good monitoring. But I don't think, as far as the rich suite of scientific capabilities, I don't think there are many places that are that good.
And not even New Jersey. They've got Rio.
No, they'll catch up. I mean, they're really good. In fact, one of my subcontractors for that big observatory thing I talked about is Rutgers, and that's the reason I did it, because they know what they're doing.
Yeah, who at Scripps is in charge of doing the study of offshore falls?
Yes.
And where is that? And what issues do you see are going to become a problem to getting it done?
Getting what done?
The study, the seismic study?
Oh, the seismic stuff. Yeah, I actually, you saw a geophysicist there. I'm a seismologist. And in fact, I've done a lot of work in the last few years with tsunamis in particular, and I'm on a National Academy committee that's called Fukushima Lessons Learned. And one of the obvious goals of that is to look at Fukushima, see what happened there, how does that translate into U.S. regulatory issues, and so on. There are faults in the basin in Southern California. They are not particularly long or very capable. There's no long history of very large events from these earthquakes offshore. There's nothing like the Japan Trench and the fault off Japan, for example, off Southern California, or even until you get right to the north in Northern California. So those kinds of things don't exist, don't happen. But we talked about the stuff that's in the ocean. There's even a much, much larger system ashore that is measuring seismic events and using global positioning system to actually measure ground movement over time. So it's very well instrumented. Again, the data are open in real time. These things do, and I didn't make that part of the story, but in the future we need to make the onshore fit with the offshore so that we have the same people, the same guy and ideas working both places. But it's a good place to live. LA is not particularly great. San Diego, Hawaii is a great place to live because there aren't many earthquakes.
We're going to take one more. Bill.
You mentioned Hyperion outfall, and there's a major work pending.
I think there is. This was back in 2006, and I think they learned a lot when they repaired it last time that is going to require another visit, but I don't know anything about the schedule right now.
We'll give you one more. You get the last.
These outfall lines, is the discharge at the end of the line, or is there places along where?
Well, I show you there's this Y thing, and that discharges along those Ys. It doesn't all go out to one place. It diffuses into the water column and is generally carried south to La Jolla and Mexico.
And so we discharge about 2.1 billion gallons a day of wastewater through these discharges along the coast. And except during the rainy season, it's the largest source of fresh water in the Southern California Valley. But now, before we transition, so John, I think so far my hypothesis is all right. Scientifically, there's no part of the world ocean where we know as much, where there's rich a database, where you guys have developed as many toys to study the ocean, and they're then used all over the world. And so it's not the lack of scientific understanding that gets in the way of making appropriate, sustainable uses of the ocean.
No, well, there may be. I mean, but I don't. The kinds of things we usually talk about, I think that we have the data necessary to make most of the decisions, but it's not necessarily ever looked at in the decision. I mean, that's where the politics takes over.
Thank you very much.
Thank you.
All right, now our next speaker came all the way from India to be here with us. But it was 3 years, when he was 3 years old when he came. This is Dilip Khatri. He is a structural engineer with URS Corporation. He's an expert on structural engineering, wind and solar energy. Prior to joining URS in 2008, he was principal at Khatri Inc. for 19 years. He received a BS in civil engineering from Cal State Los Angeles, MS in structural engineering from Caltech, MBA in finance from USC's Marshall School of Business, and a PhD in structural engineering from USC. He also, I lost my other note, was at professor for 10 years at Cal Poly.
Yeah.
At Cal Poly, Pomona.
Right.
And wonderful range of experience. And so Dilip is going to talk about engineering in the Southern California Bight. And I hope that we will focus on the state of our capacity for engineering within the Southern California Bight. Use some other examples, but we really want to know what your take is on how sophisticated we are here.
Thank you.
Please join me in welcoming Bill Cowdery.
Thank you very much, and thank you to the Aquarium for inviting me. It's a pleasure to be here. Thank you all for sparing your evening to join us. I enjoyed the first presentation. I thought that was really excellent. Thank you so much, and I certainly learned a lot. My topic today is to talk about wind energy, and this is a fairly hot topic these days, both in the science and engineering world, but also politically. It's been mentioned quite a bit in the last couple of debates. Some of those comments I'd like to answer tonight, since I thought that they were not answered properly in the debate. So I'd like to extend, and since I'm not a politician, I hopefully will give you an answer. Wrong one. Oops, sorry. How do you get the pointer? And the pointer? You got it. Thank you. Thank you. Okay. So I want to first give you a little overview of wind energy. And again, I encourage you to ask questions as we go through. I'll do my best to answer. I was a faculty member at Cal Poly Pomona for 10 years, so I'm used to dealing with a rough crowd. You seem to be a lot more docile. So I want to tell you a little bit about the overview of the wind energy industry, some of the basics of the technology. There's a lot of misunderstandings, I think, or just basic ignorance about what wind energy is. Tell you a little bit about new turbine technology, what's going on in the industry, and what's dealing with specifically offshore, which is the reason that I thought that topic would have specific relevance to the class tonight. And then a little segment that I put together on some papers that I've published over the last, recently over the last 10 years on solving the world's problems with wind energy, and see if we might be able to stimulate some interest there. If we look at the wind energy industry in the United States, it's about a $12 billion industry. And it's been growing. I mean, in the last, much of the growth has occurred over the last 7 years. And you know, that may seem like a very exciting number. It is an exciting number, especially since I've been in the industry for almost 15 years now. When I started working in the wind tower industry about 12, 15 years ago, we were well under $1 billion a year. Now we're at 12 billion. We're nothing compared to the oil and gas industry. Just to give you a relative comparison, that $12 billion annual sales is the total revenue of the entire industry in terms of turbine sales, volume of traffic. If you look at the annual revenue line of ExxonMobil, if you don't know, just one company, their annual revenue line is about 350 billion, just one company. So we're not anywhere in that league, but we are growing. Right now, we're in a state of uncertainty, particularly up until the November election, because one of the key elements that supports our industry is the production tax credit, which is right now kind of up for grabs. It's up for renewal at the end of December. And if it doesn't get renewed, then we're going to take a bit of a dock, come January. There'll be a slowdown for at least 6 months, maybe a year. Yes?
I was just going to say, I was talking to somebody, and they said usually they bundle solar and wind together. Do you know any reason why they decided to separate the two? Was it a divide and conquer sort of thing? Or?
No, it wasn't a divide and conquer. The reason is that solar, there's a slide which I'll talk about it, but I'll address your question. Okay, let's look at the whole U.S. energy market, right? 100% of the U.S. energy market. 50% of the United States energy comes from coal, okay? 25% comes from nuclear. The last 25% is a mixture of hydro and various other sources, okay? The total sum contribution of wind and solar, which gets a lot of press these days, is roughly 2% of the entire 100% pie. And out of that 2%, solar is about 1/10 of 1%. So the solar guys, we consider ourselves friends, and since I work in both industries, I don't discriminate between solar and wind. But the solar guys negotiated their PTCs with a longer period. They didn't want to get tied down with the wind guys, because the wind guys actually get the capture the bulk of the credit. So it was a business decision, but they are represented by two different lobbying organizations. But that's the reason that they unbundled them. And I'm not sure if the solar one is up for renewal. I know the wind one is.
We got it signed, I think, over the summer.
Yeah, so those guys are doing pretty good. I mean, the solar traffic is going to be good, but the wind guys right now are the ones that are. And in the renewable market, again, the wind market is still the lion's share. It's still, well, lion's share meaning of the 2%, we're 1.9%. You know, I mean, in our little small pie, if you will. We are the fastest growing segment of the power market. I mean, we are definitely growing. So I want to first dispel some misunderstandings and give you a little history, okay? Because everybody says, oh, wind is a new technology, wind is new, wind is new. I always hate it when I listen to that because it's not new. We outdate all of them. We've been around, wind has been around longer than nuclear, coal, and all the rest of the guys combined. And we didn't start as windmills, but we started with sailboats. And we go back, actually it's more than 5,000 years, it's 7,000 years. There's nothing new about wind power. It's been known for centuries, okay? Modern day wind power started back in the 70s. It started with small 225 kilowatt, 660 kilowatt turbines on 30 and 40 meter towers. And they've been used for decades on ranches and agricultural land in the 10 kilowatt, 50 kilowatt range just to supply power for pumping water, irrigating farmland. But it's not a new technology. There's nothing here that's new. This has been around for quite some time. And there's plenty of proof in the history books, okay? So it's an old technology that's been around for centuries being reworked for modern day, using modern day turbine technology. So as we've progressed through the industry through the past 40 years, the wind market has really made a substantial change since the year 2000. I think that's when things really started to change for the wind energy industry, because then it made a transition from what I call small mom and pop type operations into the major corporation environment, where now you have major companies that are involved in wind energy. You have major oil and gas companies that have created divisions of their company to invest in wind. And so that's been a big change, hopefully for the better. The turbines have gotten larger, the blades have gotten bigger, the towers are getting taller, and we'll talk more about that. So again, looking back over the last 40 years or so, we've gone from 1 megawatt turbines on 60 meter towers to projects which were 30 to 50 megawatts. We've now got tremendous interest from the investment banking, from insurance industry. We've got more access to capital. And the primary driver has been the production tax credit. And I want to spend a few minutes and talk about that and kind of answer some notions on that in a moment. There's a lot of production tax credits. There's a whole variety of them. And there was one comment that was made in the first debate, which kind of got under my skin, and I want to talk about it, where one of the candidates, Governor Mitt Romney, made a comment, and he said that President Obama has pumped $90 billion of tax credit into the renewables in 1 year. I don't know if you remember that comment, but he said that like 3 or 4 times. And he said, 90 billion, 90 billion. You know, that's too much money, that's too much money. I'd like to say a few words about that, okay? Yes, that may be true. First of all, I'll question the 90 billion, but I'll take the number at face value and make it 100 billion. How much investment has been made in our hydroelectric dams over the span of the last 80 years? If we take the aggregate investment in the Hoover Dam and all the dams that have been built in the western United States, I'd like to know how many billions of dollars that is, which we are now enjoying the benefits and the fruits of that investment made back in the 30s and the 40s. But if you took that aggregate investment and put that in today's dollars, it's a far cry from what we're asking for in the wind business. And there is a benefit, there is a return that comes out of it. So you can't just say that when we put a production tax credit into a particular industry that we're only going to value that one annual contribution you've got to also look at the other industries that we're competing against and look at the total aggregate investment that's been made in those segments of the industries for the last 50 years in order to make a fair comparison. And it takes time. If you were to take a project like the Hoover Dam and say, okay, we're going to invest so many hundreds of millions of dollars or billions of dollars in building a dam, and if it doesn't break even in the first 5 years, it was a waste. I don't think that's really the right way to make the evaluation. You've got to look at the power, the cost of power today, which has been amortized over the last 60 years of the life of that infrastructure. And so we have to keep things in perspective that, yeah, there's a production tax credit. Yeah, you're making an investment, but there's also a return that comes over a period of time. So I wanted to add that comment to the discussion. And what is the contribution right now? I mean, how does it work? Okay, so I'll tell you what the production tax credit is, and I'm going to walk you through a simple example of what it really means in real dollars. We're going to take actually a one turbine example and walk through the numbers with you. So the US has about 2% power generation from wind. President Bush discussed going with 20%. He wanted to see 20% in 20 years contribution. That's where that 20 in 2020 came from. The governor of California has actually signed legislation, I think, which is more aggressive than that. I forget what the numbers are. I think it's 30% or something like that. RPS standards, one of the most aggressive standards in the country. So to answer the theme of Jerry's comments about Southern California, this is the right place to be going renewable. You've got the political will is there. You've got one arm of the government saying do it, and you've got the other arm saying stop. Okay, so now what we need to do is get the two arms working together, and then we can probably do something. But there's definitely the political will to get it done is definitely high in this state. And I do work in a lot of different states where definitely California is not one of the friendliest states to do business in. But in terms of resource, in terms of the wind resource, and in terms of the population center, we definitely have that. And we have the technology for sure. And we'll talk more about that in a second when I get to the examples. At the end of the day, when you put up a wind power plant, the cost of producing wind power, it comes out around 7 cents per kilowatt hour. That number varies depending upon the location of the plant, the topography, the terrain, the location. And if it's offshore, that number goes from 7 cents to roughly 10 cents per kilowatt hour. If you're building in Texas, which doesn't have any hills and your grading cost is real low, that number drops down to around 3 cents per kilowatt hour. The government tax credit, and forgive me, I think the 2 cents is a mistake. I think it's 1.5 cents. So I beg your pardon, I may have made a typo. I think it's about 1.5 cents. It might be 2 cents, I'm not sure. Is a credit given to the developer for doing green energy. So you may say, well, that's a subsidy. It's a tax credit. I kind of view a subsidy a little bit differently. A subsidy is more like a grant that is written off. This is a tax credit. So it's a write-off to the investor against their taxable earnings that they have to pay. It's a credit. It's not a check that they write to you. Now, there was a 30% grant that was in effect with the Obama administration that expired last year, where that was in effect up until the end of 2011, where anybody that built a renewable power plant got 30% of that cost, basically a check from the federal government. So that stimulated quite a bit of growth. But right now, this is the big one. This is the one that is right now on the table right now, which is currently not being renewed at the moment because nobody's talking to anybody until after the November election. Okay, so these numbers are a little bit out of date. I didn't have a chance to update them, but they give you at least a ballpark. Our biggest friend in the industry right now is Texas. Oops. Our biggest friend in the industry right now is Texas. Texas loves wind energy. Iowa is a very big proponent of wind energy. We've got California, Minnesota, and Washington. And so these numbers are relatively the same. I think California may have moved up to second place in the last 2 or 3 years. But in the ballpark, that gives you kind of an idea of where the rankings are between the states. I'd like to talk a little bit about the technology of how energy is actually generated. How does it actually work? So the energy is captured from the wind flow going across an airstream. And if you think of the wind turbine, which has a certain blade diameter, think of that as a tunnel, if you will. That tunnel is carrying a certain volume of air, which is traveling at a certain velocity. And those of you that are physics or engineering scientists, majors, understand the term of kinetic energy. It's the mass of the particle times the velocity squared times 1/2 gives you the kinetic energy. So in that airstream, you have a certain amount of energy. That energy travels across the swept area of the blade. And the turbine is attempting to capture that airstream of energy, okay? So in a perfect world, we would love to capture 100% of the volume of energy, which is theoretically available by Mother Nature. Due to engineering restrictions and a lot of math, which I won't go into, we've proven mathematically that there is a maximum efficiency that you can capture from that airstream. It's called Betz law, and it's 57%. You cannot capture more than 57% of the airstream energy. So how does it capture the energy? Well, as the air passes through the blades, which are the same concept as an aircraft wing, has an airfoil. And that airfoil adjusts its pitch. And based upon the attack angle of the wind, it will lift the blade. It will create a lift. When it creates a lift, it causes the blades to rotate. And so on the upside, the blades are positioned with a certain pitch, and they're lifting, they're turning the turbine. On the downside, the blade can readjust its pitch, because otherwise if it remains at the same pitch, it would be causing drag. So one of the biggest technologies that have been developed in the last 5 years is the variable pitch, variable frequency wind turbine. I'll just quickly explain that, and then I want to show you some pictures. The old technology, the blades were fixed pitch, meaning that they were just stuck at a certain angle. So when on the lifting side, they would work very well, but then on the downside, they would cause drag. But because they were fixed pitch, you couldn't do anything, so the blade would only generate power at one rotational frequency. And you either got that power or you didn't get that power. You either reached a certain wind speed or you didn't get it. So they made them very inefficient. Nowadays, the new technology, the blades are adjusting their pitch as they turn around. Very sophisticated. They're pitched on the upside to catch the lift, and then on the downside, they're pitched in order to reduce the drag. And then they have variable frequency, so they can rotate at different frequencies depending upon what the wind is doing. So it's become very, very sophisticated turbine technology, yes.
You mentioned the 57% efficiency. Is that regardless of the size of the blade? You know, because the turbines are different sizes.
Yes, that is independent. That's a mathematical maximum efficiency.
Same with cars.
Same with cars? Yeah, I can't comment on the cars. Yeah, okay. Yes?
Are the old style blades been replaced by the new style?
You can't replace the old ones because it's not just replacing the blades. There's a whole actuator system. It's not like changing the wheels on a car. You know,
But could you replace the whole hub unit? You know, like out in Palm Springs, you know, there's a lot of dead ones.
Trust me, you don't want to go there.
Okay. It's easier to start over.
Take my word, it doesn't work.
Yeah.
You can't do it. You can't take a Honda Civic from 1989 and put a turbocharged engine in it and say, yeah, the Civic's going to work. Because there's the whole drive mechanism and the differential and the suspension and everything.
Well, the stressing of the tower.
Yeah, so it just doesn't work. So you have to go with a whole new tower. Okay, so the rotation of the blade creates an angular momentum, which is then inside the generator, is converted to electrical power using a system of magnets and electromechanical energy conversion. So you have the same technology that's used in a hydroelectric dam, except that there they use water. Same exact principle, except that there you're using water, here you're using wind. So you have the blades rotating, and then this is just a schematic showing the nacelle, which is the actual generator. There's all kinds of new technology occurring in the generator design, all kinds of neat stuff happening in the wind power business. People coming up with bigger generators. Just to give you an order of magnitude, we started again, 40 years ago with 100 kilowatt, 200 kilowatt systems. We're now up to an average turbine right now is 3 megawatts. One turbine is 3 megawatts. The average offshore or nearshore turbine is 4 to 5 megawatts. The biggest turbine being developed right now, there's 3 companies developing a 7 megawatt turbine, and there's 1 company developing the first 10 megawatt turbine. I'd like to tell you a little bit more about that later, because then it gets into the discussion that Jerry brought up of economic revitalization in California, which this 10 megawatt turbine has a great story to it that I want to share with you. Yes, sir.
Just out of curiosity, how many homes would be powered by just 1 megawatt?
I knew you were going to ask me that question.
Just so I get a scale of how much the 10
And you know what? I got a slide just waiting for you. It's coming your way. After the next commercial break, we'll be right there. Yes, it's coming your way. Yes.
You mentioned in a place like Texas where there's no hills, you lose the cost of grading, so your cost per megawatt hour goes down.
Yes.
What about in these offshore, nearshore turbines? How does the cost of installation factor in?
Yeah, I quoted you a number. It goes up to about 10 or 11 cents per kilowatt hour. And I've actually done one example of an offshore turbine because we're actually working with one of our favorite clients who's sitting right here in the second row, the Port of LA, where we're actually looking at a study for them to possibly do this. So we've actually done an example. And so I'm going to walk you through that in a few minutes. Okay, so here's my, oh wow, it worked. Sometimes I'm impressed. Sometimes my slide actually works. Okay. Oops. I spoke too soon. Okay, so there you see that schematic of the airstream. Okay. And the blade then trying to capture that power. So you haven't asked the question, but I always get asked this question: why do they have 3 blades? Okay. And the simple dumb answer is they've already tried every other type of blade configuration. They've tried 5 blades, they've tried 4 blades, they've tried 2 blades. There is one company that still does the 2-bladed, but most of the companies, 98% of the wind turbine companies, have arrived on 3 blades as being the most optimum. And there's a number of reasons for that, which I don't want to go into. You could spend a whole week just talking about blade technology, but it has to do with the balance of the loads. The 3-bladed is a very well-balanced design, and the 3-bladed is where you get the best efficiency. Okay, the 2-bladed, there is one company, I don't want to discount them, there's one company, Nordex, which produces a 2-bladed turbine. Nobody does a 4 or a 5-blade, and what we found is that the more blades you add, you increase the drag, and so your efficiency actually starts to drop. Okay, now the next curve over here. So as the wind starts to blow, and your turbine is standing there, as the speed of the wind starts to pick up, we have the first stage, which is called the kick-in, or the cut-in velocity. That's when the blade starts to turn. That's the beginning of your power generation. And so that speed, which is confidential to every turbine and blade company, because it's proprietary to each. Every company has their own product spec. But I will tell you that 98% of them are about the same, okay? It's around 4 to 5 miles per hour. So your kick-in, your cut-in speed is around 4 to 5 miles per hour. That's when you start to generate power. Then as the wind speed picks up, the blade frequency starts to increase, you generate more power, and this is called a power curve. And so you reach at some point, which is called the sustained wind speed, where you will reach your maximum power output for that turbine. And again, that number varies from all the different turbine manufacturers, and that is a very key element. It's called the power curve. It looks something like this, but when you actually, oh, let me come back to that slide. But when you actually buy the turbine, this is the curve that they give you. I actually had to strip it from which manufacturer I got it from, because it's very proprietary, it's highly confidential, blah, 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 okay? And so at a certain point, when you pass the sustained speed, and that number, again, for 98% of the turbines is somewhere between 15 and 20 miles per hour. So you kick in at about 5 and you reach your maximum efficiency between 15 and 20. Once you pass 20, 22 miles per hour, you end up with a degradation. Not quite as smooth as that. in the power curve that I showed you just a minute ago, then the turbine is actually starting to lose efficiency because the wind is starting to get a little too choppy, a little too strong. Then it reaches a point where the turbine is not generating any power, it's just spinning, and now it's a hazard. Because now if it spins too fast, lots of bad things can happen, okay? Which I'll give you a clue of, but what we've done and what every turbine has is a shutdown velocity, which is the cutout. That usually is around 25 miles per hour. At 25 miles per hour, as far as I know, there's no turbine that works over 25 miles per hour. I don't think I've heard of any. So at 25 miles per hour, it shuts down. So all the notions that we need 50-mile-an-hour winds, we need 60, we don't need 50, 60-mile-per-hour winds. We need good, steady winds between 15 and 22 miles per hour. That's where we make the most use of wind energy. Anything over 25 miles an hour, right now the industry is not designed for that. So that's called the shutdown velocity, or the cutout. The amount of power that's generated is directly proportional to the swept area. The bigger the blades, the more power you're going to generate. So the industry is moving towards bigger swept area, larger turbines. And the reason is that if you want to do 20 megawatts power, before we would be doing 20 towers of 1 megawatt apiece. That's 20 times the infrastructure cost. It's cheaper to do 4 towers that are 5 megawatts apiece. Then you reduce your infrastructure, you reduce your impact on the environment, you reduce the amount of grading, the dirt moving, the crane, everything shrinks. You get more power per tower, okay? The other thing also environmentally is that the bigger the swept area, the bigger the blade diameter, it moves at a slower RPM, which is better for the birds. The smaller the blades, the faster the blades move, not good for the birds. And if it's not good for the birds, it's not good for me, it's not good for anybody else. So better to go with the larger blades, the birds can see them. And so the new technology, the 10 megawatt turbine, moves at a peak rate of, I think, 11 RPMs, 11 revolutions per minute. The old ones, the 1 megawatts and the 660 kWs, were working at 22 to 25 RPM, double the speed. So that's been done by design. It's more efficient, less impact, less environmental impact, less risk to the birds. And
there's less noise?
Less noise, yes, right. So that's the power curve, typical power curve. The old projects, utility grade projects are usually projects over 50 megawatts, turbine sizes greater than 1 megawatt. And your typical investment, $70 million plus. And the utilities, the wind power uses a gross of about 3% of the gross acreage. It's much more less environmental impact than solar. And I also do solar projects. So for example, to do 1 megawatt of solar, you need about 5 acres of land to do 1 megawatt of solar. And you can see that with 1 wind tower, you can accomplish that much more efficiently. And then projects which are under 50 megawatts, towers less than 80 meters, these are sort of what we call community wind projects. Small wind are projects that are under 100 kilowatts, mostly used on rural applications, commercial buildings, farming communities. Just an idea on costs. It costs about $2 million per megawatt for an onshore project. So a 100 tower project is going to be about a $200 million project. And they involve all aspects, all the different aspects of engineering come into play. So how do we pick where we're going to put them? Well, number one, obviously, is where there's the wind blowing, where we have a good resource. We don't need hurricane winds. We don't need 50-mile-an-hour winds. We don't need to be in a tornado zone. We need to be in a zone which is calm, where we have nice steady wind with least amount of turbulence. We want it to be accessible. We want it to be, with reasonably good property control without any issues dealing with easements or conflicts with communities and so forth, and hopefully close to some transmission. And of course, we want to partner with local community. The wind energy industry's got enough to deal with and having to deal with if the community doesn't want the project. We want to be where the community wants to have the project. We are zero carbon emission. You know, we have a zero carbon footprint compared to other sources of energy. The usual drivers are noise, visual impact, and avian and bat. And then these are the additional prominent criteria, but usually these are the three that will make or break you. Yes, sir.
Does the wave climate off Southern California coast meet your criteria then?
Yes, and I'm going to talk about that in a moment. I've actually got some proposals to kind of circulate just to keep you thinking of some ideas that I think will at least stimulate some interest, hopefully. But yeah, no, this is a very favorable place. Okay, so now we talk about offshore wind, right? Now offshore wind is really, if you took now let's go back to the original picture that I had of you, that I gave you, of the 100% energy market, 50% coal, 25% nuclear, 20% hydro, whatever, 2% wind and solar, 1.8% wind. Out of the 1.8%, how much is offshore? Anybody want to guess?
None.
Give the lady a prize. 0 for North America. For Europe, they've done, I don't know, maybe 300 megawatts. The Europeans are way ahead of us. The Europeans have seen the benefit of offshore wind, and they are moving fast. The 3 countries right now that are on the forefront of the technology, maybe 4 countries, Great Britain, primarily Scotland, Norway, and Germany. On the Asian side, it's China and Taiwan. They are moving like gangbusters. They want to capture the technology. Now, I'm going to share with you some inside stories on that in a moment, but first I want to give you the physics of why offshore wind is such a big benefit. The main thing is that because you're near the ocean. And the reason is, and it doesn't take a genius to figure this out, is that the ocean has a very low skin friction. And so the wind velocity traveling over the surface of water has less drag than the wind traveling over land. Over land, you have friction, which slows the wind down, obviously, on the surface of the land. And so your wind profile changes dramatically when the wind hits the surface of the land. And so you have to go up with higher towers. The ocean, if you're near the coast, you have less surface skin friction, so you get a better wind profile. You don't have to go as high. That translates into a very economically beneficial project when you're close to the coastal environment. So let me throw some numbers on the table. If you're doing an onshore wind project, now remember, 57% is the mathematical high that you can get. You cannot get anything above that. So your average efficiency factor for onshore wind is around 25%. If you got an onshore project, a land-based project that's got an efficiency factor, we call it capacity factor. If your capacity factor is 30%, that is a great project. That's a winner. Anything over 30% is exceedingly great. I mean, that's above average. So you're between 25 and 30%. The capacity factor for an offshore project or coastal project starts at 40%. So you're at least 35 to 40% on your capacity factor, and I've seen them as high as 45% for some of the projects off the coast of Scotland. Now, I'm going to share with you the economic benefits in a moment because I've got an actual numbers example to share with you. But you've got no obstructions, you've got no building interference or vortex flows, you have less turbulence, and you can build closer to the ocean surface. You can do a 60-meter tower rather than doing a 100-meter tower. And you can generate more power, and all the turbines for offshore are geared for larger scale applications. No one's going to do an offshore turbine with 1 megawatt. It doesn't make sense. They're going to do it for at least a minimum 4 megawatt, preferably 5 to 7 megawatt size turbine. Yes.
When we talk about the size of the tower, you have to get up above the water level.
Yes.
And
Yeah.
How deep of water are these usually put in?
Right now, the majority of the projects are in shallow water, which is 20 meters or less. Well, there have been 2 projects done in deep water, but those are floating turbines. They did the first 2 in the last 3 years.
Didn't they try some on some old oil rigs too that were already in place?
I'm not aware of that.
Yeah.
I don't think that that's been done. I could be wrong, but I don't think so, because the reason is that the last people that I would expect to be helping us would be the oil and gas industry. They're not our friends for the most part. Yes?
Well, doesn't building that in a wet marine environment add cost? Because,
Yes?
yeah, I mean, you can't just put a land turbine in the water.
No, you cannot. And I'm going to get to the numerical example in a moment. But I wanted to first set the stage of the physics as to why offshore makes sense. Okay, so there's all kinds of new types of foundations right now being talked about. There's the floating, these are all floating platform systems. The first 2 in the world have just been installed, one off the coast of Portugal and one off the coast of Norway. The Europeans have seen the benefit, they've seen the light. They're moving full blast ahead with this technology. And I will share with you just a quick anecdote of exactly how aggressive they are, okay? The 10 megawatt turbine conceptually was developed by a California company, right here in Santa Barbara. The company's called Clipper Wind Power. They developed the concept of the 10 megawatt turbine to be designed and built in Southern California in their Santa Barbara facility. Okay, this was started, I don't know, 5-6 years ago. The government of Scotland came in and said, hey, Mr. Clipper, how about if we give you a little incentive and you move your power plant from California over to Scotland? Remember, now this is a California company. And of course, we know what kind of reception he was going to get if he went to the governor in Sacramento about getting an incentive. So the state of Scotland wrote him a check for £7 million to develop their turbine technology under the condition that the research and R&D would be developed in Scotland. So what do you think they did?
Bought some sun lamps and went to Scotland.
They set up a whole plant in Scotland.
Yeah.
They hired about 100 people there. And that's currently being developed. The 10 megawatt turbine is being designed and developed in Scotland to be built and manufactured in Scotland. The company's still here. Clipper is still here in Santa Barbara. But they're missing one thing to their design. They don't have a tower. They got a turbine, but they don't have a tower, which is what I'm trying to talk them into, is to design their tower. But the Europeans are way ahead of us. They'd like to steal that tower technology also and put that over there too. Okay? So this shows you the aggressiveness that's going on right now. The Chinese and the Taiwanese right now have already got proposals going to do the first tentative offshore wind farms. So it's very aggressive right now. The Norwegians, one of the world's largest oil companies, Stat Oil, just finished the installation of the very first floating wind turbine tower, which is basically a big pole with a ballast in the North Sea. They spent $70 million to do one tower because they want to own that technology. They want to own that technology because they see the application. Okay, so we have issues. These are different types of foundations. Right now, what we're looking at, what I would propose for Southern California, particularly for our coastal environment, is baby steps. Let's start off with the basic shallow water turbine, maybe medium depth with just a basic monopole. That's already been built by the Europeans. They've already got them in operation. It's been done, it's been proven, and it can be done here. So I've already talked about all this. I'll just quickly recap. I talked about the wind shear, more consistent wind, less turbulence, more efficient power production, the cut-in speed about 4 to 5 miles an hour, shutdown of 25 miles per hour, and the best winds are between 15 and 20. Okay, so here's some numbers to get back to the gentleman who asked the question about how much does one turbine generate. We're going to get to that in a moment. But here's a quick overview. So you take I've taken one tower of a 5 megawatt capacity. Okay, just one tower. It's going to generate with a 40% capacity factor. That's not an aggressive assumption. That's at about an average assumption. Okay, about 17,500 megawatt hours. in 1 year. And I'll tell you what that means in terms of power per house, so to speak. But let's first look at the revenue side. If you're paying around 12 cents per kilowatt hour, which I think is somewhat of the norm, I don't know what LADWP charges. I'm just quoting something that from my power bill. I live in Pasadena, and I'm paying around 12 to 15 cents per kilowatt hour. Now, I don't just look at the power cost. I also lump in all of the other extraneous charges, the tax and the this thing and the that thing. Add all that up and divide by your kilowatt usage to come up with how much you're paying for the power, because that's what you're really paying.
Yeah.
So it's between 12 and 15 cents. Again, I have not been aggressive. Okay, I'm not trying to be a salesman. I'm just trying to give you the numbers just to show you what they look like. That comes out to about $2.1 million per year in terms of the value of what that tower is generating. It's got a 20-year life, so again, using pretty nominal assumptions, not aggressive assumptions, just average conditions, one 5-megawatt tower is going to generate about $42 million of revenue over a 20-year time frame. I have been very conservative on the cost. I've taken the highest number that I heard at the last conference. The real cost is going to be somewhere around $4 to $5 million per megawatt, but I have taken the highest number just to be on the safe side and said that that one tower would cost $30 million to build. It's about $6 million per megawatt. That's the highest number that I heard, and that's what I used. The real number I think will be around 3 or 4, but let's take the highest number and let's go with it and see what we come up with. So you got, and again, I haven't factored into interest or time cost of money or inflation. I'm just looking at revenue cost, just using present value. The production tax credit, and I did use the 2 cents, which may be high, but fine. It may be like 5 cents once we go back and look at it again. The production tax credit is worth about $350,000 a year using the 2 cent. And so for 20 years, that comes in at about $7 million. If I'm off by a couple million, it would be around $5 million if I'm mistaken on the 2 cent. So your net cost, instead of $23 million, may be around $25 million, okay? But you've got a positive cash flow that the turbine would generate power and make money. Even without the production tax credit, it would still make money. The problem is that without the production tax credit, it's hard to get private equity to look into this. But a public entity, a port or a city or a government agency which doesn't benefit from the production tax credit would definitely look at this. And we haven't factored into the environmental benefit, the carbon emission cost, the opportunity cost, if you will, or the environmental cost of going and generating this power using fossil fuels and other conventional technology, which there is a cost associated with that, as we've already heard from the previous speaker. There is a cost associated. I haven't factored in, I'm just looking at the project standalone as it is. So one 5-megawatt turbine. Now here's what I did. I just took my power bill because I didn't have anybody else's power bill. So my house, I use about 1,000 kilowatt hours a month. It's a bit of a hog, okay? I use a little too much power. But, so my house is a little bit big power bill. So it's about 12,000 kilowatt hours per year, 12 megawatt hours a year. So the one turbine would power about 1,400 homes of my size. I think for a conventional home or apartment, you know, with less power demand, you're going to be somewhere around 2,000 homes with one 5-megawatt turbine. So that's just one tower, right? Okay, so that gives you a little bit of the background and the math, and then I wanted to talk a little about some ideas that I've proposed in some of my published papers about solving some of the world's issues, several of them which we have right here in Southern California. And one of them, which has been studied quite a bit, it's not my idea by any means. It's already been studied by NREL, National Renewable Energy Lab, is creating fresh water using wind power merged with desalination to desalinate ocean water. It's actually the perfect blend because one of the biggest complaints about wind power is that it's not consistent, that you don't have consistent winds. Now, for the ocean environment, that can be challenged because you do have consistency in the ocean environment and in the coastal environment. But if you were to use wind power to be merged with desalination and put it on a coastal environment, I mean, what a great solution for solving the issue of water. And water is a major, major issue of the environment. And so here in Southern California, we happen to have a bit of a demand for water, and we are in a desert. I couldn't see a better application for wind power right here in Southern California to help supply us with fresh water on a consistent basis. And so people will come to me and say, well, hey, wait a minute, that's really expensive. You're going to put these wind towers, you're going to convert ocean water into fresh water. Well, where do we get our water now? We go, 500 miles, 700 miles, and we built an aqueduct to bring it from the Sierras? And then you're telling me that I'm crazy? Give me a break. We've already built that. And if you took, and would be the next part of the paper that I would like to write, is if you took the infrastructure cost of that aqueduct, and I'm not saying that we should, it's already been built, folks, it's done. It's already there. Nobody's saying we should shut it down or remove it or take it off the grid. But it's already done. So let's take I'd like to know what the infrastructure cost of that aqueduct is in today's dollars, divided by the cubic yardage of water that's pumped into Southern California to keep our population alive. And compare that cost per cubic foot of water compared to a simple idea like this where the water's right there. And then think about the additional cost of the environmental damage that's caused from bringing that water all the way from the Sierras, plus we haven't made many friends up there by doing that, as opposed to just taking the water here from the ocean. And this could be applied worldwide. You've got this issue of fresh water applies worldwide. Coastal populations in India, in the Sahara Desert, in Saudi Arabia, off the coast of Africa. I mean, just that one solution right there could change a lot of things. Yes, sir.
Could you imagine Mulholland trying to pull permits today?
Well,
We'd still be working on the groundbreaking.
it's, and again, no, I'm not putting down the solution that was proposed, that's what they had at the time.
Yeah.
But let's think about what that cost was and is in today's dollars before we start disputing this cost. I'm pretty sure, and I haven't done the numbers, but being an engineer that I am, I will at some point to put it in the paper. I'm pretty sure that the infrastructure cost per cubic yard of water to do this is going to be a lot cheaper than doing the aqueduct and comparing that cost. And we could use that water to fill our reservoirs. And the water's right here. It's right there. You just need to desal. Okay? So, and this has already been studied. This is not an original idea. I didn't come up with this. This has already been studied by NREL. They've got papers already published on it. They've been talking about it. And what a great place to do something like that in Southern California or anywhere along the coast of California. You've got a huge population center. You've got the wind resource there. You've got the water, and you're a desert. It wouldn't make sense to do something like this in upstate New York or on the East Coast because they've already got plenty of source of water already there, and they're not as hungry as we are. They're not a desert environment. Okay, and then think about the cost of transporting that water. Coastal power. Okay, this is another great application of wind power. By putting wind power offshore by 2 or 3 miles to create a reliable source of clean power. So the first question I get when I raise that question is, we don't want to wake up in the morning and look at a bunch of ugly wind towers. I don't think that they're ugly, but that's okay. We all have our own taste, okay? I understand, okay? In Europe, they look at it very differently. When they see a wind tower, they think, oh, they're saving the world. Americans look at a wind tower and they say, who was the schmuck that approved that? Okay? So I'd like to change that perception, but I want to give you some math to think about. If we were to think of it in 2 miles offshore, that's about 10,560 feet. A 100-meter tower, and we probably won't need a 100-meter tower, but let's use a 100-meter tower because it's an easy number. And we ratio that, it's about 0.03106. If you think of a yardstick, now take your 2 miles and now condense it down to a yardstick. That's the equivalent of about 1 inch, 1.1 inch high on a yardstick. If you put in 3 miles, it drops to 3/4 of an inch. So, I mean, I don't think we can even see 3 miles sometimes, off the coast of California with some of the weather that we have. I don't even know if you can even see them. So, I think that that's a solvable problem as far as the visual impact. Yes?
The only thing is if you put it, off the coast of, let's say, Palos Verdes, if you go out 3 miles, all of a sudden you're in, 400, 500 meters of
Yes, yes.
How does that factor in? Is there a trade-off between visibility and cost?
Yes, there is. We do not have a continental shelf like they do on the East Coast. But I'm not thinking necessarily off the coast of Palos Verdes. I've got another proposal in here, which is kind of using some areas near Catalina, which I'll talk about in a moment. And again, they're just ideas, folks. You don't have to, come after me after the speech. There's no proposal before the governor or anything. It's just, these are just floating ideas, excuse the pun.
But we already have plenty of oil rigs to look at, so.
Well, that's what I like to say. When people always dish my wind towers, I always say, okay, well, if you don't want the wind tower, I guess we'll have to give you a nuclear power plant. That's the best we can do.
Or another oil rig offset.
Or another oil rig, if you're going to dish my towers, then I guess we go back to the nuclear and everybody can glow in the dark.
Well, we're going to have to get power someplace.
You got to need power from something, and I think this is the cleanest, most efficient, and cost-effective way to get there. If anything, at least increase the percentage from 2% to something, reasonable. We've got an impact, an environmental impact. Okay, I'm running out of time. 22 miles. Okay, so here's another idea. Santa Catalina. I was just at Catalina 3 weeks ago. Catalina is completely powered by diesel. All of their power comes from diesel fuel. It's not a big power demand, but boy, do they have a fantastic wind source. What a great place to put some wind towers. And it's a beautiful island. Nobody said we had to put it on the front end where the boats come in. You can put it on the other end and not only serve the power demands of Catalina without any problem whatsoever, not only serve the water demands of Catalina Island without any problem, but possibly even create a source there of power for the mainland. And so people will come back to me and say, that's 22 miles, you got to put an undersea power cable, what are you, nuts? Are you crazy? 22 miles, how much is this going to cost? Okay, we're bringing water 700 miles. I don't understand why you're picking on me for 22 miles. You want to bring water from the Sierras, you can you're bringing power from the Hoover Dam on the Colorado River. That's, 300 miles, 400 miles? You're bringing the power from there. I don't see what the big deal is for 22 miles. And islands in particular are a great candidate for wind power. Because if you look at the cost of wind power on islands, I'm working right now on a wind project in Hawaii, on the island of Maui. And the cost of power depends on which island you're on, but I think it's somewhere between 50 cents to $1 per kilowatt hour. On the Cayman Islands, they had an RFP, request for proposal, that was out about 3 years ago. The Cayman Islands, fully powered right now by diesel generators. That's all the islands are powered by diesel. And the Cayman Islands does not have a very big power demand. They just wanted to get 10 megawatts. So they put an RFP out for wind power companies to come and submit a proposal to do 10 megawatts. With the numbers that I gave you, that's like 2 towers, maybe 3, okay? You could power the Cayman Islands. Because
Offshore or onshore?
Onshore. They're onshore, but because Cayman Islands being an island, that if you're close to the sea, it's as good as offshore in terms of efficiency. But you're not physically offshore necessarily. But you can go offshore if you want, just to get, for visibility or for whatever, natural resources, just to protect the environment, whatever reasons you want. The Cayman Islands was paying about $1.10 to $1.50 per kilowatt hour. So imagine now if we could do wind power there for 10, 15 cents per kilowatt hour. That's it's a great project from a money standpoint, but it's also environmentally conscious, and you eliminate the use of this diesel fuel and all the carbon footprint and all. So take that example, and now you can multiply that by how many islands there are in the world. There's a lot of potential there. I'm just proposing for Santa Catalina because it's here, it's in Southern California, and I think it's an idea that should at least be looked at. Offshore floating platforms. Now this is, again, as I said, the 2 countries that are taking the lead on this, I should say 4 countries: Norway, Scotland or United Kingdom, Spain, China. Actually, I'd also say Germany, maybe 5 countries. They've already developed offshore floating platforms. They've already built the first 2. What a great way to power some of our Navy vessels, which are all working on fuel, on carbon producing. Again, not so much of a crazy idea. You can have an offshore wind platform within the proximity of a Navy ship and supply that with power. At least supplement its power and cut down again on your fuel consumption and your carbon emission. Ports and harbors, which we're working on right now with the Port of LA, looking at using wind tower generators to supplement their existing demand for power. Okay, and again, anything which is coastal has the potential for being a good project because it's in the vicinity of the coast. It's got a good resource. The wind is there and the ocean surface is there. Irrigation of desert lands. Well, Southern California, you may not agree with me, it is a desert, okay? So you may question the fundamental logistics of why somebody decided to put a major population center in an area which doesn't have any water. We've supposedly solved that problem, but we still go through periods of drought, and we shouldn't be surprised because it's a desert, okay? We don't actually, California cannot sustain its own population based on its current natural resource. It never would have had this population. The water has to be brought here for the population. So again, using wind power to irrigate the desert lands, to create water not only for drinking water, but also water for irrigation of the farmland. Another great source which wind power lends itself very well to. So the Europeans are way ahead of us. The Chinese, the Taiwanese, Norway, Portugal, they've already completed their first prototype project. The US has projects that are on the books. So here's where I want to make my pitch for the West Coast. Because right now, all of the talk of offshore is on the East Coast. And I just got back from a conference on the East Coast on offshore wind. All of the attention right now is on the East Coast because they have major population centers, they have a continental shelf. All of the projects that they proposed on the East Coast, none have been built yet. They've been in planning and permitting for 10 years. All of those projects are big projects. They're 100, 200, I think 300 megawatt size projects. Great idea, fantastic ideas. I hope that they can build a few of them in the next 5 to 10 years. I hope that I can actually see them. There's one question, though, which I asked my friends on the East Coast, which nobody wanted to answer me, okay? I wrote it down, but nobody wanted to talk to me about it. Have you done a risk study for these wind towers subjected to hurricanes? And boy, they didn't like that. They didn't want to hear from me on that question. This is something that the West Coast has the advantage on. We don't have this problem. And I think that, again, I don't want to slow them down on the East Coast, but I don't think anybody's actually looked at that. And putting a beautiful wind farm off the coast of the Chesapeake Bay is a great idea, and I'm all for it, and I hope they succeed, and I hope they can do it, or off the coast of Florida, and they've got some planned over off the coast of Texas. But when that first hurricane comes through and blasts that area, I think there's going to be some serious rethinking in terms of the investment component of the infrastructure cost. This is a problem that we don't have. We have another problem, which is earthquakes, but we can actually design for that. I don't think anybody's actually looked at the impact of hurricane winds on wind towers. That's something that needs to be investigated. But it is, I hope and I promote that they will be successful and that they can hopefully lay the groundwork for us to move forward. Thank you. Oh, and I do have one short film since, I think I have a few minutes, yeah. So one short film, we're going to show you, we're going to build a wind tower for you in 4 minutes. Take a look. right.
We got
Thank
time
you.
for a couple, Dylan.
Okay.